interpretation of IR spectrum. Now, with the IR spectrum, we'll not be able to completely identify the structure of the compound, but at least it will give some clues, or the IR spectrum will be able to justify the structure of the compound. Now, let's take a look into this compound, which has this spectrum. So we have 2-methyl-1-pentene, which has this structure, and this is the IR spectrum of this compound. First, to begin with, we are going to find the carbon-hydrogen stretching frequencies. So for which we are going to drop a line around 3000 centimeter inverse. So here is 3000 centimeter inverse, and we can see that there are peaks on the right side and also on the left side. Okay, these peaks on the right side is going to correspond for the sp3 carbon hydrogen stretch, and this one on the left side, since they are close to 3100, it's going to correspond for the sp2 carbon hydrogen stretch. Now, since we know that this molecule has got sp2 carbon, we need to identify whether there is an alkene or benzene in the structure. So for which we are going to look around 1600. There is a peak missing around 1600, but in the case of benzene, we also need to see another peak around 1500 centimeter inwards. So between 1500 to 1430 centimeter inwards, but that peak is also missing, right? But we do see a peak, like one intense peak around 1650, which may correspond to the C double bond C. Apart from that, we also see a peak around 890, and this peak around 890 centimeter inverse is going to correspond for the terminal alkene that is connected to two R groups, right? So from the compound, from the structure, we can clearly see that we do have sp3 carbon hydrogen bonds and sp2 carbon hydrogen bonds, right? So this is going to be the sp2 carbon hydrogen bond. And we also have carbon-carbon double bond. And we can definitely say that we do have a terminal alkene. So this alkene is basically a terminal alkene, which is connected to two R groups. One is a methyl group and the other one is a propyl group. And obviously, we can tell that this spectrum corresponds to this molecule, 2-methyl-1-pentene. Let's go on to the next example. Here we have benzaldehyde. So again, let's apply the same principles, same rules. Again, we are going to draw a line around 3000. So here is 3000. Now we do not see any peaks on the right side of 3000. Okay, so which means there is no sp3 carbon hydrogen stretching. Okay, but we do see peaks on the left side, which can correspond to the sp2 carbon hydrogen stretch, which is around 3050 centimeter inverse. Okay, so next is when you go in this region. Okay, so this is about 2800 and 2700. So there are two peaks around that region. So that's going to correspond for the sp2 carbon hydrogen stretch present in an aldehyde. So this is going to be carbon hydrogen stretch that is present in an aldehyde. Okay, so one is around 2800 centimeter inverse and the other one is around 2700 centimeter inverse. Once we know that we have sp2 carbon, we need to find out whether this carbon-carbon double bond is from the alkene or from the benzene ring. So when you drop a line right here around 1600, yes, we do see peaks around 1600, and also we do see peaks around 1460, right? So these two peaks right here is going to correspond for the C double bond C present in the benzene ring. Okay, and then finally, we also see a peak around 1700 centimeter inverse. That's going to correspond for the carbonyl group present in the aldehyde. So this is going to correspond for the carbonyl group present in the aldehyde. So with all of this, we can definitely say that this is the spectrum of benzaldehyde. For the third example, we have 2-propyne, 1-ol. Here is the structure for this molecule. So let's find out what are the absorption bands, what are the important absorption bands that we can look for this compound. So we should definitely be able to see a peak corresponding to OH, a peak corresponding to C triple bond C, and also for sp3 carbon hydrogen stretch, and finally for the sp carbon hydrogen stretch. These are the important absorption bands you're going to look in the IR spectrum. So first, to begin with, here is going to be the absorption peak for OH, and since this is an alcohol, we have talked about that it's going to form hydrogen bonding, because of which this band can be really broad. Okay, so this is going to correspond for the OH. Now let's drop a line around 3000. So here is 3000. Now we are able to see peaks on the right side of 3000, which is definitely going to correspond for sp3 carbon hydrogen stretch. This should not be confused with the peaks that's present in the carbon hydrogen stretching frequencies of aldehyde, because this is not close to 2800, right? So this is going to be for sp3 carbon hydrogen stretch. And we do not see any peak around 3100, which means we do not have any sp2 carbon hydrogen stretch. But we do see a peak around 3300. This is going to be corresponding for sp carbon hydrogen stretch. You can imagine that this peak for sp carbon hydrogen stretch has been buried inside the absorption band of OH. Okay, and then so we found that this is going to be around 3300 centimeter inverse. We already found that there is a peak for sp3 carbon hydrogen stretch. We already found out that there is a sp carbon hydrogen stretch. And then we needed to find out the carbon-carbon triple bond. The carbon-carbon triple bond is going to show up around 2100 centimeter inverse. Remember, a carbon-carbon double bond is going to show around 1600 centimeter inverse. Because carbon-carbon triple bond is stronger, it's going to show up at a higher frequency, which is around 2100 centimeter inverse. Okay, so this peak right here is going to correspond for the C triple bond C. So with all this, we can definitely confirm this is the spectrum of 2-propyne 1-ol. The final compound that we have is ethyl benzyl ketone. So let's do our job here. We are going to drop a line around 3000. We are able to see peaks on the right side and as well as on the left side. And the peaks on the left side is close to 3100, right? So we can say that this is going to correspond to the sp3 carbon hydrogen stretch, and this one right here is sp2 carbon hydrogen stretch. So once we know that we do have sp2 carbon, we need to find out whether it's from the benzene ring or from the alkene. So for that, we are going to look around 1600. We do see a peak around 1600 and also another peak around 1500. So both of these is going to correspond to the benzene ring, the C double bond C present in the benzene ring. And then we do see a peak around 1700. This is going to correspond to the carbonyl group. And then we also have a methyl group, so for which we are going to look in this, look around this 1400. On the right side, we do see a peak around 1380 centimeter inverse, and this is going to correspond for the CH ben present in the methyl group. So with all of this, we can definitely justify that this is the IR spectrum of this compound.